In this video, we're going to be going over some angular momentum formulas. So, first we have angular momentum is equal to the cross product of vector r cross p. The magnitude of this is going to be L is equal to mvr sine of theta. Now, if you have a rigid body, your angular momentum is going to be the inertia times the angular velocity. Let's say that you have a point mass moving past a pivot. So this happens when a particle flies by a point, and also your impact will matter in these parameter problems, and also when you have scattering. When we examine these three, our algebra setup is going to be angular momentum is equal to the mass times the velocity times the lever arm r perpendicular. If we know that the v is perpendicular to the radius though, you can just write L is equal to mvr. If not, you need the previous. If not perpendicular, then you have to use L is equal to mvr sine theta. This is what we'll tackle, that component. Remember that only the perpendicular component of velocity matters. Next, let's talk about a rigid body rotating about a fixed axis. When you have this will usually be when you have a point mass where the inertia is mr squared. Your setup is going to be angular momentum is inertia times the angular velocity. Point mass is, again, I equals mr squared. A rod, this is at the center. That's going to be I is equal to 1 over 12 ml squared. A rod at the end, that's going to be I is equal to 1 over 3 ml squared. If you have a disc or a cylinder, that's going to be I is equal to 1/2 mr squared. And if you have a hoop, that's going to be inertia is equal to mr squared. Now, let's review. What is the conservation of angular momentum? This is when we have the condition that your external torque is going to be equal to 0. You set initial angular momentum equal to the final. Then for your rigid body, you can represent this as inertia initial is equal to angular velocity initial is equal to inertia final times the angular velocity final. So this is for like when you have a figure skater pulling their arms in, or you have rotating stools or collapsing systems. So rotating stools, collapsing systems. Now, what if we have a changing shape? If you have a changing shape, that is when your moment of inertia changes. So when it changes, that's when you have like a clay block that hits a disc, or when you have a bullet embedded in a rod, embed in a rod, or a mass landing on a platform. So they stick, lands. Again, you can write the initial is equal to the final, And the initial, we have mvr. Finally, we have the inertia of the object plus mr squared times the angular velocity. So that is the final equation. So what you get to note here is that energy is not conserved, and the angular momentum is also not conserved. Well, now let's talk about what if you have an explosion or a separation in rotation. So that happens when objects break apart, when masses fly outward, and that's also when you have no external torque. So this is going to be like when you have your initial is equal to your final 1 plus final 2. This is because we have two objects. So if it's initially at rest, then you can write the initial is equal to m1v1r1 minus m2v2r2. Then you can add this to the other side, and you have m1v1r1 is equal to m2v2r2. And the signs, they matter. The reason why is because they're opposite, because they fly in opposite directions. So they split apart. Now, what about angular impulse? So what this is torque applied for time. When do we see this? We see this when you have a rotational collision. Also, when you have a torque versus time in a graph. And also, when you have a short torque interval, when you're examining it over a brief amount of time. So that's when you have delta L, angular momentum, is equal to the torque times the change in the t, time. LF minus L initial is equal to the torque times the change in time. I times moment of inertia times the angular velocity final minus I angular momentum initial is equal to the torque times the change in time. Now, what if you have torque and you also need to find angular acceleration, but they're not conserved? So when this happens, this means that we're going to see motors also breaking wheels. And also that means that we have external torque. So this means that you're going to set up the summation of the torque is equal to dl over dt. Now for a rigid body, we can write the Newton's second law in rotational forms. That's the summation of the torque is equal to the moment of inertia times the acceleration. And you can combine that with the angular acceleration is equal to dw, or d times the angular velocity divided by dt. Now, what if you have angular momentum about a moving origin? So you're going to have to utilize center of mass. So your vector of angular momentum is going to equal to r center mass cross mv center mass plus I cm times O times angular velocity. And this means that we combine translational plus rotation. What about when we have orbital angular momentum? Well, this is when we have planets and satellites, and also centripetal motion, which is just when it points into the center of the circle, it keeps it moving in a circle. So that's, you have L equals mvr. Now we can say that our angular momentum conserved, m1 vr, m1 v1 r1 is equal to m2 v2, or just m, we only have one mass, m v2 r2. Solving for v2, then we just divide, we get r1, the m's cancel out, so then you get m's cancel out, then you get r1 over r2 times v1.